In orbit around the Earth, we all know about the International Space Station, a symbol of international cooperation in space. But did you know that there is another mysterious fortress floating in the cosmos, rarely mentioned in Western media? It is Tiangong, the space station developed and operated by China since 2021. The experiments and projects taking place here are not only extensive, but also hold surprising secrets about China's space ambitions, from how humans adapt to microgravity environments to previously unpublished physics discoveries. In this video, I will reveal every detail you have never heard of, and trust me, you will be amazed by the scale and ambition of Tiangong. Hit subscribe and watch until the end of the video so you don't miss any important information about this mysterious world of space. Let's take a deep look at Tiangong, China's space station, to understand how their space efforts do not stop at putting humans into orbit, but also open strategic opportunities for humanity's future in space. Unlike the ISS, an international cooperation symbol that has been operational for over 25 years, China's space program is still young, having only begun in 2011 with the plan to launch Tiangong 1. What is special is that this first space station was launched as a whole unit and has a simple cylindrical design, 4.4 meters long with two solar panels on either side. It does not have the complexity of the 108-meter long ISS, but this simplicity reflects a clear strategy. First, China focused on mastering the technology of assembly and module connection in space, while testing the basic capabilities to sustain human life in orbit. Tiangong 1 demonstrated the ability to maintain life, operate a small laboratory, and receive both crewed and uncrewed spacecraft. During nearly 7 years of operation, it laid a solid foundation for the next steps. Following this success, Tiangong 2 was launched in 2016 with the mission to test and perfect key technologies for a larger space station. Its goal was not only to conduct microgravity experiments, but also to evaluate stability, long-term operational capability, and efficiency of scientific modules. When Tiangong 2 completed its mission and left orbit in 2019, China officially entered the stage of constructing a large-scale space station, Tiangong 3, with the ambition of turning it into a center for research in science, medicine, robotics, and space manufacturing. Tiangong 3, often simply called Tiangong, includes the core module Tianhe, where the crew lives and works, along with two science modules, Wentian and Mengtian. Wentian focuses on studying the effects of space on living organisms and developing medical technologies, while Mengtian examines physical phenomena in microgravity environments, such as fluid behavior, combustion processes, and heat distribution. The solar panels rotate towards sunlight to maximize energy intake, while the robotic arm outside supports extravehicular activities, bringing astronauts to areas that need operation. The entire station is 55 meters long, weighs 100 tons, and can accommodate up to 6 taiwanauts at a time. Smaller than the ISS, but still requiring in-orbit assembly of each module, Tiangong has demonstrated China's rapid progress in managing sophisticated orbital systems. Life on the Tiangong space station is also carefully tended. The astronauts are provided with up to 120 types of space food, ranging from basic dishes to traditional Chinese meals, to ensure good nutrition and morale throughout their time in orbit. Like on the ISS, astronauts must exercise daily to prevent muscle atrophy due to microgravity. But Tiangong also carries an educational mission. The crew participates in presentations, online interactions with students, helping to popularize science and inspire the younger generation. They even plant rice from the same batch of seeds grown in space, exploring how microgravity affects plant development, an important step toward farming on distant planets. Interestingly, although the experiments may seem general scientific in nature, all are aimed at a larger strategic goal: building advanced technological capabilities in a microgravity environment. There are 5 key areas of focus: orbital assembly and construction technology, robotics and automation systems, energy and new propulsion technologies, environmental control and life support systems, and general spacecraft technologies. It sounds complex, but in fact, each area contributes to expanding human activity beyond Earth. For example, in orbital construction, Chinese scientists are experimenting with 3D printing ceramics in microgravity, a significant step toward manufacturing parts and structures directly in space instead of transporting them from Earth, thus reducing cost and risk. They are also developing expandable inflatable structures, lightweight and easy to transport habitats applicable on the moon or other celestial bodies. Robotics also play a crucial role. Just like automated production lines on Earth, robots in space are tested to perform assembly, repair, transport of materials, and support tasks for the crew. Taionauts on Tiangong have participated in many microgravity experiments with robots, laying the groundwork for building automated facilities in the future. Additionally, China is researching new energy and propulsion technologies, including optimizing solar energy usage and preparing alternative energy sources for missions farther from the sun, where sunlight is much weaker than in Earth orbit. Looking at the whole picture, it is clear that Tiangong is not just a research station. It is a launch pad for China's long-term ambitions to build production, living, and exploration capabilities in space. Every experiment, module, robot, or test structure is aimed at creating a solid technological foundation from Earth orbit to nearby planets and celestial bodies. And importantly, everything happening on Tiangong is designed to pave the way for humans to live and work long-term beyond Earth, an ambition that just 10 to 15 years ago was only an idea. Looking beyond Earth's orbit, it is clear that China is not only preparing for near-term missions, but is also considering ambitious projects on distant planets and asteroids within the solar system. One of the greatest challenges of expanding human activity in space is energy and fuel. Carrying all the fuel needed for long journeys is not only expensive, but also creates a massive burden for each flight. Therefore, any technology that allows in situ fuel extraction is of extremely high strategic value. It is precisely from this need that self-sufficient space stations become invaluable platforms for humanity's ambitions in space. On Tiangong, Taionaut astronauts not only live and work, but also test oxygen and water recycling systems, waste management, and crop cultivation, all aimed at building self-sustaining habitats. Growing rice in microgravity, seemingly a simple experiment, has strategic significance. If humanity wants to survive long-term beyond Earth, we need to learn how to sustain ourselves using local resources, from water and air to food. A recent breakthrough on Tiangong is the artificial photosynthesis experiment, in which Taionauts produced oxygen and the hydrocarbon ethylene from carbon dioxide using a semiconductor catalyst. This not only regenerates breathable oxygen for the crew, but also creates a potential fuel source for rockets. Scientists even hope to apply this process to produce methane, formic acid, or sugars, directly simulating the functions of plants on Earth. What is special is that this technology operates efficiently at room temperature, consumes little energy, and can function in microgravity, unlike traditional oxygen electrolysis techniques that consume up to 1/3 of the ISS's energy. This is a significant step forward, opening the possibility for sustaining long-duration missions from the moon to more distant planets, such as Mars. These experiments are not limited to theory. In microgravity, fluid dynamics, pressure, and physical reactions occur completely differently than on Earth, so direct orbital testing is irreplaceable. From gas recycling and waste treatment to in situ fuel production, every experiment aims at self-sufficiency in space, building sustainable bases where humans can live long-term. Looking further ahead, this could help establish networks of outposts on the moon, asteroids, and other planets, where humanity can extract local resources and even manufacture new spacecraft from off-Earth materials. It is noteworthy that China does not maintain absolute secrecy about these ambitions. They advocate international cooperation, inviting scientists from around the world to participate in joint experiments and research on Tiangong. However, legal barriers from the United States and budget constraints in Europe make it difficult for American astronauts or some other nations to participate directly. Nevertheless, opening up collaboration sends a clear message. Tiangong is not only an internal research station, but also a platform for testing technologies that could serve all of humanity. Looking at the fields of research currently underway, it is clear that China's ambitions go beyond merely constructing a space station. Artificial photosynthesis, in situ fuel production, construction and assembly robotics, 3D printing facilities, environmental control systems, energy sources, and new propulsion technologies all are directed toward a long-term vision. Humans not only traveling into space, but living, working, and sustaining themselves beyond Earth. This marks a turning point in the approach to space, unlike simply sending astronauts to the moon and returning as in the past. While the ISS demonstrates the power of international cooperation, modular engineering, and energy management, Tiangong opens a new approach where experiments not only serve basic science but also aim at self-sufficiency and in-space production. This difference is evident in how Taonaut astronauts work with robots, test gas and fuel recycling, grow plants, and control living environments. Each small experiment contributes to the overall picture, the ability to build long-term habitats on distant planets. Overall, it is clear that China is preparing for a new era of space exploration. If these technologies succeed, they will help humanity move beyond the confines of the moon and Earth, opening possibilities for living on multiple planets, extracting resources from asteroids, and even manufacturing spacecraft directly from off-Earth materials. This is not only a technological leap, but also a strategic turning point, shaping how we will live, work, and move in space. Although the ISS remains a symbol of science and international cooperation, the experiments on Tiangong indicate a new path, where space stations are not just research facilities, but launch pads for the long-term survival of humans in space. From testing robots, energy and infrastructure, to artificial photosynthesis and fuel recycling, everything points to a distant vision. Humanity is no longer just a guest in space, but will become residents, capable of living and exploiting resources on distant worlds. These steps, although not yet recognized or participated in by all countries, demonstrate the level of progress and ambition of China in this field. Tiangong is not just a space station. It is a strategic laboratory where every theory about survival, production, and space exploration is practically tested, paving the way for humanity to truly become a spacefaring species. To maintain continuous operation in orbit, a space station requires extremely sophisticated systems. The solar panels not only provide power when directly illuminated, but also ensure electricity during periods when the sun is obscured by the Earth. Most of this energy is ultimately converted into heat, so the station needs large radiators capable of dissipating up to 70 kilowatts of heat into space, keeping the internal environment stable and safe for astronauts. Inside the station, pressurized living areas are designed and divided into Russian and US orbital segments, creating a multinational living space where systems from various technical cultures coordinate seamlessly. Building a massive structure like the ISS is not accomplished overnight. The first module, Russia's Zarya, was launched into orbit in November 1998, serving as the crucial nucleus, equipped with 3 docking ports ready to receive future modules and solar arrays. Just a month later, the US Unity module was launched from Kennedy Space Center, connecting to Zarya to begin the era of global space cooperation. Unity was equipped with pressurized mating adapters, PMAs, to connect the US port to the Russian port and to the space shuttle, creating a flexible network for assembling subsequent modules. The shuttle's robotic arm, called Canadarm, became a key tool in this process. It could attach to the 12-ton Unity module and position the Zarya module correctly to connect electrical and mechanical systems. Every operation had to be performed slowly and precisely to the millimeter, as a small mistake in microgravity could have severe consequences. Once the modules were aligned and successfully connected, the space station officially took shape. However, these 2 modules were not sufficient for human habitation. It was not until July 2000 that Russia's Zvezda module was launched, carrying life support equipment and basic living quarters for 2 astronauts. Later that year, the Z1 truss module was attached, preparing the station for habitable segments. In November 2000, the first crew of 3, Yuri Gudzenko, Sergei Krikalev, and Bill Shepard, arrived, becoming the first residents of the ISS. From that moment, the station has been continuously inhabited, laying the foundation for long-term orbital experiments. During the initial months, astronauts operated the main systems, inspected each module, and prepared the infrastructure for upcoming laboratories. In April 2001, the Canadarm2 robotic arm was launched, enabling the movement of heavy objects around the station without the need for spacewalks. Later, the Dexter device was added to assist with assembly and maintenance tasks, increasing the efficiency of the robotic system. Over the next decade, modules from Russia, Japan, Europe, and the US were launched, expanding living quarters and laboratories. Research aboard the ISS spans multiple disciplines: space biology, astronomy, physics, chemistry, medicine, and space weather studies. The ISS is not only a living space, but also a survival laboratory in space. In prolonged microgravity, the human body undergoes significant changes. The musculoskeletal system atrophies, bone density decreases, the heart contracts, and muscle strength declines. Therefore, high intensity exercise regimens are meticulously planned, along with fully equipped gyms, helping the crew maintain physical fitness. Still, no equipment can fully simulate Earth's gravity. Astronauts must relearn to walk upon return. Not only humans, but other organisms also react differently in microgravity. Bacteria, such as Salmonella, exhibit altered gene expression and sometimes increased virulence. Fire and fluids also present unique challenges. On Earth, fire rises due to convection, but in space, it spreads in all directions and can persist longer than normal. This requires safety systems to accurately calculate heat propagation and control combustion. Fluids in microgravity also do not behave according to normal rules. Bubbles can collapse suddenly, generating shock waves and posing risks to equipment. Studies of fluid dynamics, heat transfer, and bubble collapse are not only academic, but also help understand cosmic phenomena, from fire behavior in space to supernova events. For instance, the collapse of bubbles in microgravity can provide a model for the asymmetric collapse of a star's core. Thus, the ISS becomes a unique laboratory where physical laws that we thought existed only in distant celestial bodies are recreated in orbit. In addition to biological and physical research, the ISS carries advanced instruments such as the alpha magnetic spectrometer, used for astronomy and particle physics studies. These experiments, though challenging and intricate, form the foundation for all future long-duration missions, from flights to the moon to months-long journeys to Mars. In summary, operating the ISS is an extraordinary engineering and scientific achievement, where every element from power systems, robotics, laboratories to crew health management must function flawlessly in the harshest environment humans have ever encountered. It not only advances understanding of physical and biological mechanisms in microgravity, but also serves as a stepping stone for humanity to truly become an off-world species. Every experiment, whether small or large, contributes to a future where humans are no longer limited to Earth, but are progressing into the vast expanse of space. One of the most important satellites in the history of modern science, rated by NASA on par with Hubble, is a clear testament to the power of human technology and imagination. This satellite is an advanced particle detector, an essential part of a cosmic particle accelerator designed to observe particles of matter in space that terrestrial accelerators cannot reach. The voids of space are not completely empty. They contain hidden objects, particles with energies equivalent to a baseball speeding through space, millions of times stronger than what the largest accelerators on Earth can produce. This is the mission's objective: probing dark matter, a mysterious component making up to 27% of the universe, by searching for hypothetical particles such as neutralinos, predicted by supersymmetry theories. Meanwhile, on the ISS, NASA's Cold Atom Laboratory is exploring the frontiers of quantum physics. This device can cool atoms to temperatures of just 1/millionth of a Kelvin, creating a Bose-Einstein condensate, the fifth state of matter in microgravity. On Earth, these condensates quickly collapse under the influence of gravity, but in space they float stably and persist for extended periods. The crew has even created atomic bubbles, macroscopic quantum structures previously existing only in theory. These advances not only open new understanding of quantum physics, but also provide the foundation for atomic interferometry tools, potentially complementing LIGO in observing gravitational waves, especially at frequencies LIGO cannot detect. Other ISS modules also play essential roles in applied scientific research. Japan's Kibo module, with its outdoor platform, carries advanced sensors to observe Earth from space. Hyperspectral cameras collect data across the full visible spectrum, imaging oceans and coastal areas, providing crucial information on climate change and ecosystems. This data far exceeds the capabilities of conventional cameras, as it not only captures RGB images, but also analyzes physical and chemical properties of Earth's surface. Thus, the ISS not only helps us look outward into the universe, but also deepens our understanding of our own planet. The complexity of the ISS is further illustrated by how the station maintains orientation and balance in space. Using gyroscopes and counter-rotating flywheels, the station can maintain stable orientation without continuous thrusters. The simple yet highly effective principle of Newton's laws is fully utilized, allowing the ISS to hold its position in orbit without being affected by minor environmental disturbances. This is a valuable lesson for next-generation space stations, where orientation stability is a prerequisite for scientific missions and operations. In the context of the 2030s, the ISS will complete its final mission, deorbited and safely destroyed over the Pacific Ocean. Although the station will no longer physically exist, the knowledge and inspiration it provides will continue to shape space exploration. The station is not only a symbol of international cooperation, but also an essential stepping stone for humanity to enter an era of deeper exploration, from the moon to Mars. Private companies like SpaceX and Blue Origin are preparing to play major roles, while international space agencies plan for next-generation stations, such as Orbital Reefs and Gateway, the Lunar Orbit Space Station. Gateway is a milestone in NASA's space ambitions in collaboration with Roscosmos, JAXA, and CSA, aimed at creating a space station not only in Earth orbit but also around the Moon, serving as a transit station and habitat for crews. It will combine crew cabin modules for astronauts preparing for missions with research and support modules for robotic and human missions. Gateway's construction relies on the Space Launch System (SLS), NASA's most powerful rocket ever built, capable of delivering 130 tons to low Earth orbit, ensuring sufficient payload to assemble each module and necessary equipment. However, SLS is an expendable rocket with launch costs estimated at $2 billion per mission, making the development and deployment of Gateway controversial, but also a testament to NASA's exceptional ambition. Building Gateway is a long process, expected to be completed no earlier than 2026. Each module will be launched into orbit, assembled, and tested, gradually enabling support for the Artemis missions, sending humans to the Moon and eventually to Mars. This means Gateway is not just a transit station, but also a survival base, where crews can conduct research, prepare, and resupply before undertaking deep space missions. Leveraging experience from the ISS, NASA, and international partners can apply lessons on power systems, life support management, robotics, and scientific experiments to Gateway, ensuring efficiency and safety. The ISS and subsequent missions like Gateway demonstrate one clear point. Space exploration is no longer the domain of a single nation. It requires cooperation, long-term vision, and the ability to apply cutting-edge technological advances. Every experiment on the ISS, from particle physics, dark matter, BEC, gravitational wave detection, to climate and ecological observation, serves as foundational building blocks for long-duration space travel and future space station projects. In summary, the ISS is not just a space station, but humanity's laboratory, where knowledge, technology, and the spirit of international cooperation converge. It opens the possibility of understanding the universe in ways previously only theoretical, while laying the groundwork for future adventures, from Earth orbit to the Moon and beyond. And it is from these lessons that humanity truly steps into a new era where the boundary of imagination is the only limit to capability. Fortunately, thanks to Gateway's flexible modular design, NASA can expand the space station in phases, based on the actual needs of future missions. This capability not only allows Gateway to adapt to long-duration missions, but also minimizes risk and cost during deployment. While NASA aims to reach Mars in the 2030s, all plans depend on allocated budgets, the progress of initial missions, and policy stability. However, with competitive pressure from China, a nation accelerating its ambitions to explore the Moon and deep space, NASA's continued advancement seems inevitable. This new space race, although driven by science, also carries commercial value and potential military strategic significance, leaving no party willing to fall behind. The first phase of Gateway focuses on fundamental but essential elements: energy and propulsion modules that will ensure the station can operate independently and be ready for expansion. The Halo module, intended as the basic habitat, will allow a crew of 4 to reside for at least 30 days. This marks an important turning point in transforming Gateway into a flexible space hub where the crew can live, conduct research, and prepare for deeper space missions, including to the Moon and Mars. Alongside building Gateway, NASA will deploy a rover to the Moon's south pole, a region confirmed to contain hidden water ice beneath permanently shadowed craters. This rover will map the water in detail and assess its purity, preparing for long-term settlement projects. The South Pole was chosen not only for the presence of water, but also because of the perfect combination of deep shadows and craters, protecting ice from sunlight, and abundant sunlight on surrounding peaks, providing optimal conditions for solar panels and potential crop cultivation. However, surveying and extracting ice from these craters is no small challenge. The rover must move precisely, powered solely by batteries, into the crater, collect data, and return before the batteries run out. Recharging with solar panels requires extremely accurate calculations, and the rover's design will be decided through a NASA competition, leveraging the most creative ideas from companies and research teams. Once Gateway is deployed and operating stably, Artemis 3 will transport the crew to the station, expanding living space via the Orion module. This will provide scientists the opportunity to observe the effects of space radiation on the human body outside Earth's protective magnetosphere. These short stays will assess exposure levels and test protective measures, while 2 astronauts will land at the Moon's south pole to conduct ice surveys and other scientific experiments over approximately 1 week. Among them is expected to be the first female astronaut to set foot on the Moon, equipped with advanced spacesuits significantly improving mobility compared to Apollo missions. Thanks to this flexibility, the crew can move more easily, bend their legs, and conduct experiments on the lunar surface more efficiently than ever before. The knowledge gained from Artemis 3 will form the foundation for NASA to build a self-sustaining moon colony. From oxygen production, water recycling, to crop cultivation in a limited environment, every improvement will be tested near Earth, shortening feedback time and reducing risk compared to more distant missions. The Moon becomes an ideal testing ground due to its low gravity, proximity, and resources, such as water ice and helium-3, a valuable element for future nuclear fusion reactors, which can be harvested for Earth and other space missions. The Moon also enables the production of advanced materials, such as metal foams, more easily thanks to low gravity. On Earth, this process is difficult because bubbles in molten metal tend to rise and burst, but on the Moon, the porous structure forms uniformly, with higher quality and lower production costs. Once the material is ready, transporting it back to Earth is easier due to weak gravity, or it can be launched into orbit via electromagnetic launchers for retrieval by spacecraft, opening unprecedented commercial and industrial prospects. After Artemis 3, NASA plans to conduct 4 additional missions, gradually expanding Gateway, turning the space station into a hub for moon missions, while preparing infrastructure and experience to send humans to Mars. The coming years will witness intense competition in space exploration, particularly as China advances its own space program. This will be a challenging yet highly exciting period, where science, technology, and human ambition converge. These efforts are not only scientific, but also inspire future generations, emphasizing the importance of international cooperation, creativity, and adaptability to harsh environments. Gateway and its related missions are living proof that with imagination and determination, humanity can open new frontiers in space, from exploiting lunar resources, building self-sustaining colonies, to preparing for deeper exploration of the solar system. As we look back on the journey of building Gateway and the Artemis missions, one thing becomes clear. Space is no longer merely a place for exploration. It has become a global challenge, a measure of human cooperation, intelligence, and willpower. Gateway is not just a space station, it is a stepping stone, a research hub, and a roadmap for missions farther afield, from the Moon to Mars. The step-by-step installation of energy modules, habitats, and propulsion systems reflects a highly practical scientific philosophy: advance incrementally, manage risks, and prepare for long-term expansion. Every launch, every module attached to Gateway is proof of the close coordination between engineering, science, and international project management. The presence of humans at Gateway and on lunar missions carries significance far beyond science. It provides an opportunity to understand the human body in high radiation, low gravity environments, and the long term effects of radiation exposure on health. From testing protective systems to experimenting with life support and survival equipment, each mission offers invaluable lessons. This knowledge will be crucial as we move toward months long journeys to Mars, where humans will face extremely harsh conditions. Beyond survival, Gateway serves as a massive laboratory where experiments in physics, chemistry, materials science, and biology are conducted in microgravity. Researching ice at the moon's south pole, testing oxygen production systems, recycling water, and cultivating crops under limited conditions are all essential preparations for building self-sustaining colonies. This combines basic and applied science, research to understand the universe, and research to serve humanity, ensuring that each mission provides not only data, but practical living experience for astronauts. An important aspect not to be overlooked is global competition. As China and other nations accelerate their space programs, maintaining a leading position in this field becomes a strategic priority. Gateway and the Artemis missions are not only scientific symbols, but also evidence of humanity's creativity, international cooperation, and technological prowess. This race, while competitive, simultaneously drives groundbreaking advances in research and technology, opening unprecedented opportunities for commerce and resource exploitation. Helium-3, metal foams, and other rare materials on the moon will be strategic assets, potentially influencing the global economy, industry, and energy. From an emotional perspective, Gateway and related missions are a reminder of humanity's unending spirit of exploration. Every module, every launch, every step an astronaut takes on the lunar surface is proof of imagination, perseverance, and the will to push boundaries. As the new generation of astronauts steps onto the moon, they work not only for themselves or their countries, but carry the pride and aspirations of all humanity. This is a powerful message that the limits of exploration are defined not by technology or physics, but by our vision and determination. Gateway, Artemis 3, and subsequent missions also shape the future of deep space exploration. Lessons from the moon will become essential for Mars missions, from establishing life support systems, managing energy, recycling water, cultivating crops, to operating equipment in harsh environments. Every small detail studied, tested, and improved will contribute to reducing risks, increasing efficiency, and protecting astronauts' lives during months-long journeys into deep space. Ultimately, Gateway is not just a scientific and technical project. It is a spiritual legacy. It reminds us that international cooperation, intelligence, creativity, and perseverance can achieve what once seemed impossible. When we look up at the night sky, we see not only the moon or stars, but also the limitless potential of humanity, the ability to reach new frontiers, overcome challenges, and turn seemingly impossible dreams into reality. Although Gateway and lunar colonies will face many challenges ahead, meticulous preparation, rigorous scientific research, and international cooperation provide solid foundations. As astronauts step onto the moon, test survival systems, and survey resources, they are not only building humanity's future in space, but also inspiring the next generation, reinforcing the belief that with imagination and determination, any boundary can be overcome. Gateway, Artemis, and future projects are living proof that space is not the final frontier, but an opportunity for humanity to grow, learn, cooperate, and innovate. They remind us that no matter the challenges ahead, humans have the capacity to turn even the most distant dreams into reality. With every step taken on the moon's surface or in deep space, we are writing a new history, a history of courage, exploration, and relentless progress.